Something is happening on the Sun right now that has scientists watching their instruments a little more carefully than usual. A second coronal hole has opened up, and unlike the first one, which appeared a few weeks ago at a relatively harmless angle, this new one is pointing almost directly at Earth. To understand why that matters, you first need to understand what a coronal hole actually is. Because the name sounds dramatic, but the reality is even stranger than it sounds. The Sun's surface is not calm. It never has been. Beneath the layer of hot plasma we think of as the Sun's visible face, there are magnetic field lines threading through the entire structure, constantly twisting and looping and occasionally snapping. Some of those field lines arc back down into the Sun. Others, at certain regions on the surface, don't arc back at all. They stretch outward into space like open pipes, and through those open pipes, solar material streams out at hundreds of kilometers per second. Those open regions are coronal holes, darker than the rest of the Sun in ultraviolet imaging, cooler, less dense, and acting as launch points for something called the high-speed solar wind. This solar wind is not like wind on Earth. It is a continuous stream of charged particles, mostly protons and electrons, that flows outward from the Sun in every direction. The entire solar system is bathed in it. Earth is constantly moving through it. But when a coronal hole opens up and aligns with our position in orbit, the wind that reaches us is faster, denser, and more magnetically complex than the baseline stream we deal with on any given Tuesday. Now here is where the current situation gets interesting. Solar physicists tracking the Sun's activity over the past several weeks have noticed something unusual. The first coronal hole, which rotated across the solar disk and sent a burst of enhanced solar wind toward Earth about a month ago, was significant enough to trigger a minor geomagnetic storm. Auroras appeared at latitudes where people rarely see them. Power grid operators got a few alerts. Satellite operators adjusted their orbital drag calculations, and then the hole rotated away from us as the Sun continued its roughly 27-day rotation relative to Earth, and most people went back to not thinking about the Sun at all. But while that first hole was moving away, something new was forming. Coronal holes are not random. They tend to appear at certain latitudes on the Sun, and they tend to persist for multiple solar rotations, which means a hole that formed this month may still be active 2 or 3 months from now. Solar physicists track these regions carefully, because a persistent coronal hole that sits near the Sun's equator can repeatedly hit Earth every time the Sun rotates around to the right angle. It becomes almost like a sprinkler, sweeping its stream of fast solar wind past our planet on a regular schedule. The new hole that has opened is equatorial. It is large, and right now its orientation places it in what researchers call the Earth-directed window. Roughly speaking, that means the stream of particles it is releasing is aimed at the region of space where Earth is sitting. To understand what this actually does to our planet, we need to talk about something most people have never heard of but interact with in ways they do not realize. It is called the magnetosphere, and it is the reason life exists on Earth at all. The Sun does not just bathe us in light and warmth. It constantly tries to strip our atmosphere away. The solar wind, flowing outward at several hundred kilometers per second, carries enough energy to erode unprotected planets over geological time. Mars, which has a much weaker magnetic field than Earth, has had most of its atmosphere stripped away over the past few billion years, leaving it the thin, cold, exposed world we see today. Earth is protected by something Mars lacks at scale. Our planet generates a powerful magnetic field, produced by the movement of molten iron in our outer core. That field wraps around the planet like an invisible shell, deflecting the solar wind and creating a protected bubble called the magnetosphere. Under normal conditions, the magnetosphere handles the solar wind just fine. The particles stream around it, the field pushes back, and most of the energy gets redirected away from us. But a coronal hole changes the intensity of what the magnetosphere has to handle. The high-speed solar wind that pours out of a coronal hole is not just faster than usual, it is also structured differently. It contains magnetic field components that sometimes run opposite to Earth's own field, and when that happens, something called magnetic reconnection occurs at the boundary of our magnetosphere. The field lines on the sunward side of our magnetic bubble temporarily connect with the incoming field lines from the solar wind, and that allows energy and particles to flood in through what amounts to temporary holes in our defences. The result is a geomagnetic storm. Geomagnetic storms are measured on a scale that runs from minor to extreme, and the effects get more significant as you climb that scale. At the mild end, you get enhanced auroras. The northern and southern lights brighten and expand to lower latitudes. People in parts of Europe, North America, and the southern hemisphere who would normally never see auroras in their lives can step outside on the right night and watch curtains of green and pink light ripple across the sky. At moderate levels, the storm starts to affect technology. High-frequency radio communications get disrupted, which matters for aviation and maritime operations that still rely on those frequencies for certain communications. GPS accuracy degrades because the charge particles interact with the ionosphere, the upper layer of our atmosphere, and introduce errors into the timing signals that navigation systems depend on. At stronger levels, the effects become more serious. Satellites experience increased atmospheric drag as the outer atmosphere heats up and expands, altering their orbits in ways that operators have to constantly correct for. Power grid operators see unusual currents flowing through long-distance transmission lines, because the varying magnetic field induces voltages in anything that conducts electricity over large distances. In extreme cases, those induced currents can damage transformers, the large custom-built pieces of infrastructure that take months to replace, and that almost every modern power grid depends on. And at the absolute extreme end, which has only occurred a handful of times in recorded history, the consequences can be civilization scale. In 1859, a massive solar storm hit Earth before any of our modern electrical infrastructure existed. Telegraph systems across Europe and North America failed. Some telegraph operators reported sparks jumping from their equipment. The auroras were visible at tropical latitudes. Historians and scientists have spent years modelling what would happen if an event of that magnitude hit Earth today. With our interconnected power grids, our global satellite networks, our GPS-dependent supply chains, our internet infrastructure that runs through undersea cables that are themselves sensitive to geomagnetically induced currents. The estimates are not reassuring. Potential damage figures run into the trillions of dollars, with recovery timelines measured in years rather than weeks. We are not currently looking at a storm of that magnitude, to be clear about that, but the current coronal hole situation is not trivial, and the scientific community is watching it for reasons that go beyond routine monitoring. Part of what makes this moment unusual is where we are in the solar cycle. The Sun operates on an approximately 11-year cycle, moving from periods of relatively low activity, called solar minimum, to periods of intense activity, called solar maximum. At solar maximum, the Sun's magnetic field is tangled and stressed, sunspot activity peaks, and the frequency of solar flares and significant coronal mass ejections increases substantially. We are currently approaching, or at the peak of the current solar cycle, and solar maximum cycles are not all equal. Some are relatively mild, others are significantly more intense. The current cycle has been running hotter than most predictions anticipated. Solar physicists expected a moderate maximum, and instead they have been watching the Sun produce flares and eruptions at rates that have surprised even experienced researchers who have been studying the Sun for decades. Into this already active environment, 2 coronal holes have opened simultaneously. Now, it is worth being precise about something here, because coronal holes are not the same as solar flares or coronal mass ejections, and conflating them creates confusion about what the actual risk profile looks like. A solar flare is a sudden intense burst of radiation, primarily X-rays and ultraviolet light, that travels from the Sun to Earth in about 8 minutes. You cannot outrun it, you cannot shield against it without serious infrastructure, and the radiation effects hit the day side of Earth almost immediately. They can disrupt radio communications and affect the ionosphere rapidly, but they are brief events, minutes to hours. A coronal mass ejection is different. It is a massive bubble of magnetized plasma that gets hurled off the Sun during certain eruptive events and travels through space over a period of 1 to 3 days before potentially hitting Earth. A coronal mass ejection is what caused the most severe geomagnetic storms in history. A large, well-aimed coronal mass ejection is the thing that keeps power grid engineers awake at night. A coronal hole is neither of those things, but it produces a persistent stream of enhanced solar wind that can cause moderate to significant geomagnetic activity that lasts for days rather than hours. The hole does not close immediately, and as long as it is pointing at Earth, it continues to pour that enhanced wind in our direction. That sustained exposure is what makes a large, Earth-facing coronal hole a meaningful event rather than a brief spike. The 2 holes currently open on the Sun are being tracked by every major space weather monitoring system on the planet. The network of spacecraft that watch the Sun includes satellites positioned between Earth and the Sun that act as early warning systems, detecting the solar wind as it flows past them and giving forecasters roughly an hour's heads up before the same stream reaches Earth's magnetosphere. That hour is enough to give power grid operators and satellite operators time to take precautionary measures, adjust operations, and prepare for elevated activity. Space weather forecasting has improved dramatically over the past 2 decades. In the 1990s, our ability to predict geomagnetic storms was rudimentary. Today, the major space weather prediction centers around the world issue forecasts that look days ahead and give fairly reliable probability estimates for storm conditions. But the forecasting is still probabilistic, not deterministic. The solar wind does not travel in a perfectly straight line. It interacts with itself, with the interplanetary magnetic field, with structures created by earlier eruptions. A stream that models predict will hit Earth sometimes misses slightly. And sometimes, a stream that appears to be passing close by gets deflected in ways that bring it into contact with our magnetosphere more directly than expected. This uncertainty is one of the things that makes the current situation interesting to watch in real time. There is also a deeper scientific question underlying all of this that researchers are actively working on. Coronal holes are not fully understood. We know what they look like in ultraviolet imaging. We know they are regions of open magnetic field. We know they produce fast solar wind. But the conditions that cause a new coronal hole to form at a particular location and time, the processes that govern how large it grows, how long it persists, and what causes it to eventually close, these are all areas of active research with significant remaining uncertainty. The fact that 2 large holes have opened in a relatively short period, and that one of them is pointed at Earth, falls within the range of normal solar behavior given where we are in the cycle. But it is also the kind of event that tests our monitoring infrastructure, refines our forecasting models, and occasionally produces effects on Earth that remind us we are living inside a dynamic electromagnetic relationship with a star we sometimes forget is even there. Let us talk about those effects more concretely, because this is where the story stops being abstract and starts being about things happening right now in the world around us. The aurora situation first. When a significant stream of enhanced solar wind hits Earth's magnetosphere, the resulting geomagnetic activity often produces auroras that are both more intense and more widely visible than normal. This is not just a visual spectacle. Though the visual spectacle is genuinely extraordinary, it is also a direct diagnostic signal. Scientists use the extent and structure of the auroral display to understand what is happening in the magnetosphere in real time. Citizen scientists with cameras, distributed across the planet at different latitudes, form an informal but surprisingly valuable observational network that supplements what professional instruments detect. Over the past month, since the first coronal hole sent its stream past Earth, aurora reports have come in from places that rarely or never see them. Parts of the central United States, northern Europe at latitudes well below the typical auroral zone, southern Australia. The breadth of those reports tells researchers something about the intensity and duration of the geomagnetic activity. The current hole, if it delivers what the models are suggesting, could produce similar or greater effects. Depending on the specific magnetic orientation of the solar wind when it arrives, geomagnetic storm conditions could range from minor to significant. That is a wide range, and the honest answer is that we will not know exactly where on that range we land until the stream actually arrives, and we can measure its properties directly. The satellite situation is worth spending time on. There are roughly 10,000 satellites currently in orbit around Earth, and the vast majority of them are in what is called low Earth orbit, meaning they are operating at altitudes below about 2,000 kilometers. In this region, the upper atmosphere, even though it is extremely thin by any normal standard, is thick enough to create measurable drag on satellites. That drag is not constant. It increases when the upper atmosphere heats up and expands, which is exactly what happens during geomagnetic storms, when energy pouring into the magnetosphere gets deposited into the upper atmosphere. More drag means satellites lose altitude faster than planned. It means their orbital lifetimes are shorter. It means operators have to use more fuel to maintain their intended orbits. And it means that the complex models used to predict where every satellite is going to be at any given moment get less accurate. because all of those predictions are based on assumed drag levels that are suddenly different from reality. This matters a lot for constellation operators running hundreds or thousands of satellites in closely packed orbital shells. Getting the position predictions wrong by even a small amount creates collision risk. And in a crowded low Earth orbit environment, conjunction analysis, the process of calculating whether any two objects are going to get too close to each other, has to be rerun constantly whenever the atmospheric conditions change. The spring of a few years ago provided a clear lesson in this. A significant geomagnetic storm caused atmospheric expansion that dramatically increased drag on a large batch of recently launched small satellites. They were still in the process of raising themselves to their operational orbits and did not have enough propulsion to compensate. Dozens of them deorbited and burned up, a loss worth hundreds of millions of dollars, all because of one significant space weather event arriving at an inconvenient moment. The power grid situation is the one that gets the most serious attention in the infrastructure community. Geomagnetically induced currents, or GICs as the engineers call them, form when the rapidly varying magnetic field during a geomagnetic storm induces electrical currents in any long-conducting structure on or near the ground surface. Power transmission lines, which run for hundreds or thousands of kilometers across continents, are essentially giant antennas for this effect. Pipelines are vulnerable too. Undersea communication cables have been affected in the past. The danger to power grids is not primarily from the current itself, but from the effect it has on high-voltage transformers. Those transformers are designed to handle the alternating current of the grid, which cycles at a predictable frequency. Geomagnetically induced currents are essentially direct current, and they can push the magnetic cores of large transformers into saturation, meaning the core material stops responding linearly to the applied field. A saturated transformer draws excessive reactive power from the grid, generates unusual harmonics, and can overheat. In a severe enough event, transformers can fail catastrophically, and these are not items you can quickly replace. Large high-voltage transformers are custom-built, weigh hundreds of tons, take months to manufacture, and there is limited global manufacturing capacity for them. A scenario in which multiple transformers fail simultaneously across a regional grid is an extended blackout scenario measured in months, not days. Grid operators in regions that are geologically and geographically more vulnerable to GICs, places like parts of North America and the Nordic countries that sit on electrically resistive bedrock, have invested heavily in monitoring and protection systems in recent years. The awareness has grown, protective relays have been installed, operating procedures have been developed for elevated space weather conditions, but the protection is not complete and the risk is not zero, especially as we sit near solar maximum with an active sun producing conditions that were somewhat underpredicted by the models. The reason scientists are paying particular attention to the orientation of the second coronal hole's position is tied to something called the Parker spiral. When the sun rotates, it does not send its solar wind straight outward in all directions simultaneously. Because the sun is rotating, and because the solar wind takes days to travel from the sun to Earth, the stream of particles and magnetic field that left a particular point on the sun has already moved by the time it reaches us. The result is that the solar wind does not flow radially outward from the sun. It follows a curved path that looks, when viewed from above the solar system, like a giant spiral. This spiral has a preferred angle from which the fastest, most magnetically connected streams arrive at Earth. The new coronal hole is positioned near what space weather researchers call the central meridian of the Sun, from Earth's perspective, and it has characteristics that align it fairly closely with the ideal Parker spiral angle. That means the stream it is producing has a relatively direct magnetic connection to Earth, and the particles and magnetic field in that stream will be among the fastest and most directly delivered that the Earth encounters from this hole. The timing matters too. Coronal holes rotate with the Sun, and the window during which any given hole is in the right position to deliver its stream most directly to Earth typically lasts several days. After that, the hole rotates out of the Earth-directed window, and its effects diminish until the Sun has rotated enough to bring it back around again. So the next several days represent a period of elevated activity that is worth tracking. Here is what to actually watch for in practical terms. The Space Weather Prediction Centers publish real-time updates and multi-day forecasts. The Geomagnetic Disturbance Index, called the KP Index, is the most commonly referenced measure. It runs on a scale from 0 to 9. Values below 2 represent very quiet conditions. Values in the 3 to 4 range represent minor to moderate disturbances. Values of 5 or above represent a geomagnetic storm, with the labels minor, moderate, strong, severe, and extreme corresponding to increasing Kp values up to 9. During the period, the new coronal hole stream is expected to arrive and engage with our magnetosphere. Forecasters are currently suggesting elevated probabilities for Kp values in the 4 to 6 range, with some scenarios allowing for higher values depending on the magnetic orientation of the arriving solar wind. A Kp of 5 or 6 is enough to produce auroras visible from many mid-latitude locations under dark skies. It is enough to require precautionary measures from satellite operators and some power grid operators. It is not, in and of itself, a catastrophic event. But it is a meaningful one, and the fact that it follows so closely on the heels of the first coronal hole's activity means Earth's magnetosphere is being exposed to an extended period of elevated solar wind conditions rather than getting the recovery time that a more isolated event would allow. There is also a question of whether the coronal holes are acting as precursors to more energetic events. Active regions of the Sun, the areas of intense magnetic activity that produce sunspots, flares, and coronal mass ejections, sometimes develop in or near coronal holes. The interaction of these features can produce complex and occasionally unpredictable behavior. Researchers are watching the area around the new coronal hole carefully for signs of developing active regions that might turn a sustained high-speed wind event into something, with additional impulsive eruptions on top of it. If a significant coronal mass ejection were to form in or near this coronal hole region and erupt in an Earth-directed manner, it would arrive on top of the already elevated solar wind stream. The conditions ahead of a coronal mass ejection affect how it behaves when it reaches Earth's magnetosphere. Hitting a magnetosphere already compressed and stressed by high-speed wind is different from hitting one that has had time to recover to its normal configuration. Some of the most significant geomagnetic storms in recent history have resulted from these compound events, where a coronal mass ejection rides in on an existing elevated solar wind stream. This is not a prediction that this will happen. It is an explanation of why solar physicists are maintaining elevated attention on the current activity. Step back from the immediate event for a moment and look at the bigger picture, because that context is what makes the current situation meaningful, rather than just another space weather news cycle. We have spent the past century building a technological civilization that is deeply, fundamentally dependent on stable electromagnetic conditions. Our power grids span continents. Our communications infrastructure has moved almost entirely to digital systems that require consistent, reliable power. Our financial systems operate on networks that assume continuous connectivity. Our navigation systems rely on signals from spacecraft in orbit. Our agricultural systems depend on weather satellite data, GPS-guided equipment, and supply chains maintained by all of the above. None of this existed in any meaningful form during the most severe solar storms of the historical record. We have one significant data point from the modern era, a major geomagnetic storm in 1989 that caused a 9-hour blackout across the entire province of Quebec in Canada, damaged transformers in the United States and the United Kingdom, disrupted satellites and radio communications across North America, and produced auroras visible in Texas and Florida. That event was powerful but not extreme by historical standards. It was a fraction of the intensity of the 1859 event. The scientific and engineering communities have been working for years on improving resilience. Protective systems have been installed. Procedures have been developed. Monitoring has improved enormously, but the transformation of the power grid and telecommunications infrastructure into something that can handle extreme space weather events remains incomplete. The cost of truly hardening all of the critical systems is enormous, and the political and economic calculus of investing billions of dollars to protect against an event that might not happen for decades is a difficult one to win. This is part of why researchers communicate actively about significant coronal hole events, even ones that are not at the catastrophic end of the spectrum. The moderate events are real-time tests of the systems and procedures that would matter enormously in a more extreme scenario. They produce data that improves forecasting models. They demonstrate vulnerabilities and sometimes reveal weaknesses that need to be addressed before a larger event exposes them in a much more consequential way. Every significant space weather event that passes without catastrophe is not just a lucky escape. It is also a dataset, an opportunity to validate or refine the models, a chance to find out where the existing protections are working and where they are not. The Sun has been doing this for 4.5 billion years. It will continue doing this long after we're gone. The coronal holes that are open right now are not unusual in the context of the Sun's history. They are not even unusual in the context of this solar cycle. What makes them important is the context of what is sitting in their firing line. A technological civilization that, for the first time in the Sun's long history, can actually be harmed by what comes out of those dark, quiet openings on the surface of our star. The people monitoring this situation are not panicking. They are watching carefully, running their models, updating their forecasts, and communicating with the operators of the infrastructure that needs to be aware. That is how science works. That is how resilience is built. Not through ignoring the risk and not through catastrophizing it, but through sustained, careful attention to a dynamic system that does not care whether it is convenient or not. Over the next several days, as the stream from the second coronal hole reaches Earth and begins its interaction with our magnetosphere, the monitoring data will tell us a great deal. If the storm conditions stay in the minor to moderate range, it adds to the baseline understanding of how this particular cycle's coronal holes behave. If conditions spike higher than expected, it tests the protective systems and reveals where additional work is needed. Either way, the Sun has something to teach us, and for once, we have the instruments and the knowledge to listen. Look up on the right night this week, away from city lights if you can manage it, and scan the northern horizon if you are in the northern hemisphere. What you might see, a faint green shimmer or a dancing curtain of light across the sky, is the magnetosphere doing its job. It is the invisible shield holding back the Sun's continuous assault on the atmosphere that keeps us alive, and occasionally, when the assault is strong enough, it glows. That glow has been terrifying to humans throughout most of history, appearing as an omen of disaster in cultures around the world. Now, we know what it actually is, and somehow, knowing exactly what it is makes it even more astonishing, not less. We live on a small, magnetically protected rock, orbiting an active star that is currently pointing one of its open, magnetic wounds directly at us, as it has done countless times before and will do countless times again. The difference is that now we can see it coming. There is something worth sitting with for a moment before we move further into this story. The fact that we can see it coming is itself a relatively new development in human history, and the infrastructure we have built to maintain that visibility is more fragile and more remarkable than most people appreciate. The network of satellites and ground stations and research centres that allows a space weather forecaster in Boulder, Colorado, to tell a power grid operator in Ontario that they have roughly 60 minutes to prepare for elevated geomagnetic conditions did not exist 50 years ago. Most of it did not exist 30 years ago in any useful operational form. We built it during a period of relative solar quiet, and we're now beginning to test it seriously for the first time against a Sun that is behaving more actively than the models predicted. That tension between the sophistication of what we have built and the limits of what we actually understand runs through nearly every aspect of the current situation, and it extends well beyond the immediate question of coronal holes and geomagnetic storms. To understand what I mean, it helps to go back to the beginning of the story, not the beginning of this solar cycle, not even the beginning of modern space weather monitoring. The actual beginning, when the first person looked at the Sun and realized it was doing something unexpected. The year was 1843, and a German amateur astronomer named Heinrich Schwabe published a paper that most of the scientific community ignored for nearly a decade. Schwabe had spent 17 years obsessively counting sunspots, those dark patches that appear and disappear on the surface of the Sun, and he had noticed something that nobody else had been watching long enough to see. The number of sunspots was not random. It rose and fell on a regular schedule, completing a full cycle from minimum to maximum and back to minimum in a period of roughly 10 to 11 years. This was the first confirmation of what we now call the solar cycle, and it fundamentally changed our understanding of the Sun from a static, constant source of light and heat into a dynamic system with its own rhythms and moods. What Schwabe could not have known in 1843 was that this cycle is not primarily about the sunspots themselves. The sunspots are visible symptoms of something deeper, a global reorganization of the Sun's magnetic field that happens on an 11-year schedule. At solar minimum, the field is relatively simple and organized, with strong poles and ordered structure. As the cycle progresses toward maximum, The field becomes increasingly tangled, stressed, and complex. The polar fields weaken and eventually flip entirely, so that the north and south magnetic poles of the Sun exchange positions every 11 years, meaning the full magnetic cycle of the Sun is actually 22 years, with each 11-year sunspot cycle representing half of the deeper magnetic rhythm. This tangled, stressed field at solar maximum is what produces the increased frequency of flares, coronal mass ejections, and yes, coronal holes. The open field lines that characterize coronal holes are a product of the Sun's magnetic structure at any given moment, and a more complex stressed magnetic environment produces more of them, positioned at different latitudes, with varying sizes and durations. Understanding this helps explain why the current period is particularly worth paying attention to. It is not just that the Sun is at or near maximum, it is that this maximum appears to be more intense than the previous 2 or 3 cycles, which were relatively weak by historical standards. The last maximum, roughly 11 years ago, was so quiet that some researchers were beginning to wonder whether the Sun might be entering an extended period of low activity, similar to what happened in the 17th century, when sunspots nearly vanished for decades and temperatures in Europe dropped measurably, a period historians call the Maunder minimum. That quiet maximum made some researchers complacent about the potential for significant space weather events. The current cycle has corrected that complacency fairly emphatically. The specific mechanism that drives the solar cycle remains one of the genuinely unsolved problems in astrophysics. We know it involves the interaction between the Sun's rotation and the convection of plasma in its interior. We know the Sun does not rotate as a solid body, that the equatorial regions rotate faster than the polar regions, and that this differential rotation winds the magnetic field lines around the Sun like rubber bands being twisted. We know that at some point the stored magnetic energy gets released through sunspots, flares, and eruptions. But the precise details of how and when and how intensely, the thing that would let us accurately predict solar cycle strength years in advance, that understanding is still beyond us. What we have instead is statistical models, pattern recognition from the historical record, and a suite of physical measurements that give us increasingly good short-term predictions, but still leave the long-term picture frustratingly uncertain. This limitation matters for how we should think about the current situation. When researchers say the current cycle has exceeded predictions, they are not saying the models were incompetent. They are saying that the physical system generating the solar cycle contains chaotic elements that make precise long-range prediction fundamentally difficult in a way that is probably irreducible, not just a matter of needing more data or better computers. The Sun is telling us something about the limits of prediction, and that lesson applies well beyond space weather. There is a parallel story playing out in how we have come to understand the Sun's relationship with Earth's climate, which is a more complicated and contested territory than the geomagnetic storm picture, but one that deserves honest examination. The straightforward version of the relationship between solar activity and Earth's climate is that the Sun drives our climate through the simple delivery of energy. More sunlight means more energy in the climate system, less sunlight means less. And that is true as far as it goes, but the total energy output of the Sun, its total luminosity, varies by only about 0.1% across the solar cycle. That variation is real, and it does produce a measurable signal in Earth's climate, but it is too small to explain major climate variations on its own. The more interesting potential connections are indirect. One pathway involves the solar wind and cosmic rays. At solar minimum, when the solar wind is weaker and less organized, more high-energy cosmic rays, which are particles streaming in from outside our solar system, penetrate all the way to Earth's atmosphere. At solar maximum, the stronger solar wind deflects more of those cosmic rays before they reach us. Some researchers have proposed that cosmic rays affect cloud formation in Earth's atmosphere, and that changes in cosmic ray flux driven by the solar cycle could therefore affect global temperature through changes in cloud cover. This idea is genuinely interesting and has been the subject of significant research, including actual experiments to test whether cosmic rays can seed cloud droplets under controlled conditions. The current scientific consensus is that this effect probably exists, but is too small to be a primary driver of the climate changes we have observed over recent decades. The debate is not fully closed, but the evidence does not support it as a dominant mechanism. Another indirect pathway involves the Sun's output in specific wavelengths. Even though the total energy output of the Sun varies only slightly across the cycle, the variation in ultraviolet output is much larger, by several percent. Ultraviolet light interacts with the ozone layer in the stratosphere, and changes in stratospheric ozone distribution affect how heat is transported in the atmosphere, potentially amplifying the solar signal in ways that are not obvious from the total energy numbers alone. This stratospheric pathway is also an active research area, and the science suggests it is real but again modest in magnitude compared to other forcing factors in the current climate. Why does this matter to the story about coronal holes? Because it is part of the broader picture of how the Sun affects Earth in ways that go beyond the immediate spectacular events we've been discussing. The geomagnetic storms from coronal holes and coronal mass ejections are the acute dramatic manifestations of solar-terrestrial connection. But the Sun's influence on Earth is actually a rich layered set of physical relationships operating across timescales from seconds to millennia, and our understanding of those relationships is substantially more complete in some areas than others. The area where our understanding is most complete and most directly actionable is exactly the space weather domain we started with, and it is worth spending more time on the specific mechanisms because the details reveal something important about how the Sun-Earth system actually works. Let us go back to the magnetosphere, because there is considerably more to say about it. The magnetosphere is not a simple bubble. It is an extraordinarily complex dynamic structure that responds in real time to the solar wind flowing around it. On the side facing the Sun, the magnetosphere is compressed by the solar wind pressure to roughly 60,000 kilometers above Earth's surface. On the side facing away from the Sun, it stretches out into a long tail that extends hundreds of thousands of kilometers into space. A magnetic wake shaped by the continuous pressure of the solar wind pushing past it. Inside this structure, trapped populations of charged particles form what are called the Van Allen radiation belts, regions of intense particle radiation that circle the planet at altitudes between roughly 1,000 and 60,000 kilometers. These belts are named after James Van Allen, the American physicist whose instruments on the first American satellite confirmed their existence in 1958. What those early instruments detected was extraordinary, far more radiation than anyone had anticipated, and for a moment there was genuine concern that these belts would prevent human spaceflight. Early animal experiments revealed the radiation environment in these regions was severe enough to cause serious biological damage with prolonged exposure. The solution for the Apollo missions and subsequent human spaceflight was to pass through the belts as quickly as possible, spending hours rather than weeks at those altitudes, which kept total radiation doses to manageable levels. The astronauts still received doses that were higher than typical background radiation, but not high enough to cause immediate harm or significantly elevated long-term cancer risk, given the short transit times. During geomagnetic storms, the radiation belts change dramatically. They are not static features. The belts are continuously supplied with particles from the solar wind, and during storms the injection of particles from outside the magnetosphere can dramatically enhance the radiation intensity within the belts for days. Electrons in particular can be accelerated to very high energies during these events, creating what researchers sometimes call killer electrons, relativistic particles travelling at close to the speed of light that can penetrate satellite shielding and damage electronics. This is why the timing of geomagnetic storms matters for satellite operators in a different way from the atmospheric drag problem. Satellites in the outer radiation belt at roughly 20 to 30,000 kilometers altitude are particularly vulnerable to these enhanced radiation environments. The electronics inside them are shielded, but shielding has limits, and extended exposure to elevated radiation can cause cumulative damage, degradation of solar panels, charging effects on satellite surfaces that can create damaging electrical discharges, and bit errors in onboard computers from individual energetic particle strikes. High-energy particle events from the Sun also create hazards for humans in space and at high altitudes in aircraft. During a significant solar particle event, which is often associated with large solar flares and coronal mass ejections, but can also be enhanced by the conditions created by a fast coronal hole stream, radiation doses at polar cruising altitudes can spike to levels that require flight diversions away from polar routes. Astronauts on the International Space Station would retreat to the most shielded areas of the station during a serious particle event, and any crew on a deep space mission without the protective benefit of Earth's magnetosphere would face substantially more challenging radiation management issues. The specific challenge of deep space radiation is one of the reasons the current solar cycle timing matters for human exploration plans. There are credible programs developing concepts for crewed missions beyond the Earth-Moon system within this decade or the next, and those missions would occur during a period of elevated solar activity. The radiation environment beyond the magnetosphere during solar maximum is significantly more challenging than during minimum, and mission planners have to account for the possibility that a crew might be several days of travel time from Earth when a major solar particle event occurs. This is not an insurmountable problem. The basic physics of radiation shielding is well understood, but it requires mass, and mass is the limiting currency of every space mission. You can protect a crew with enough water tanks or polyethylene panels around a shelter area, but every kilogram of shielding is a kilogram not spent on fuel or supplies or scientific equipment. The engineering trade-offs are real, and they are being worked through actively right now by the teams designing the hardware that would take humans beyond low Earth orbit. There is a somewhat counterintuitive aspect to this problem that I want to spend a moment on, because it illustrates how the Sun's relationship with Earth's technological civilization is more nuanced than it might initially appear. The same magnetic field that protects Earth's surface from harmful solar radiation also creates the magnetosphere that causes geomagnetic storms. The same solar wind that drives those storms also deflects cosmic rays that would otherwise bombard Earth's surface with higher intensity. The same energetic particles that can damage satellites also make the auroras that are by some measure the most spectacular natural light display available to human observers anywhere on the planet's surface. The same coronal holes that are currently driving elevated space weather conditions are also part of the Sun's normal magnetic structure that helps maintain the overall stability of the solar wind flow through the inner solar system. The Sun is not malevolent. It is not targeting us. It is simply a dynamic physical system doing what physics requires it to do, and we are in its environment. The challenge and the opportunity are both exactly the same. We have built a civilization that is in a dynamic relationship with a very active star, and the choices we make about how to monitor, understand, and protect ourselves from that star's variability will matter increasingly as that civilization depends more and more on space-based and electrically interconnected infrastructure. That brings us to a part of the story that does not get nearly as much attention as the dramatic geomagnetic storm narrative, but which arguably represents the more transformative aspect of the human relationship with the Sun. We are not just passive recipients of solar activity. We are beginning to develop the capability to predict it, and eventually, potentially, to work around its worst effects in more sophisticated ways than simply shutting down transformers and waiting for the storm to pass. The forecasting story starts with a fundamental physical problem. The Sun is 93 million miles away. Even the fastest solar events, a major coronal mass ejection, travel from the Sun to Earth in somewhere between 1 and 3 days. A fast solar wind stream from a coronal hole takes 2 to 4 days. That sounds like a lot of advance warning, but the problem is that the critical parameter, the orientation of the magnetic field embedded in the incoming solar wind, cannot be measured until the stream is almost at Earth. That magnetic field orientation is what determines whether the interaction with our magnetosphere will be a gentle brush or a full-scale assault. And we cannot measure it from the Sun because it is determined by the structure of the solar wind as it has evolved over the millions of kilometers of travel from the Sun to Earth. The DESCOVR spacecraft and its predecessor ACE, which are positioned at the gravitational balance point between Earth and the Sun, roughly 1.5 million kilometers toward the Sun, are our early warning sensors. They measure the solar wind as it flows past them and relay that data to forecasting centers. Because the solar wind is moving much faster than the spacecraft itself, a stream that passes the spacecraft will reach Earth approximately 15 to 60 minutes later, depending on the solar wind speed. So realistically, we get somewhere between 15 minutes and an hour of warning before the storm conditions begin. For most purposes, 15 minutes to an hour is not very much. You cannot safely shut down a large power grid in that time. You cannot move a satellite in that time. What you can do is prepare, get into a configuration where you are less vulnerable, switch to backup systems, reduce the load on critical transformers, put crews on standby. The protection is real but partial. The goal that space weather researchers have been working toward for years is extending that prediction window. If you could reliably forecast the magnetic field orientation of the solar wind days before it arrives, rather than an hour before, the practical utility of space weather forecasting would increase enormously. That would require either developing a way to measure the coronal magnetic field directly at the Sun, which is technically very difficult because the Sun's magnetic field is embedded in extraordinarily hot plasma that is hard to probe, or placing a different kind of monitoring asset farther toward the Sun, perhaps at a position several times closer to the Sun than DSCOVR, where the solar wind would pass it earlier in its journey to Earth. Both approaches are actively being pursued. There are proposals for spacecraft that would sit at positions between DSCOVR and the Sun, farther along the Parker spiral path, specifically to give earlier measurements of solar wind properties. The engineering and orbital mechanics of placing and maintaining spacecraft closer to the Sun are significant challenges but not impossible ones, and the data from ESA's Solar Orbiter mission and NASA's Parker Solar Probe, both of which are making measurements much closer to the Sun than any previous spacecraft, are generating new understanding of how the solar wind forms and evolves that will eventually improve those longer-range forecasts. The Parker Solar Probe in particular represents a remarkable piece of engineering and scientific ambition. It has made multiple close approaches to the Sun, passing closer than any previous spacecraft, using a series of Venus flybys to gradually lower its perihelion and increase the speed of its close approaches. At its closest passes, the spacecraft is inside the Sun's corona, the outer atmosphere, where the solar wind is still being accelerated. It is measuring the properties of the solar environment in a region that was completely inaccessible to direct measurement for the entire history of space exploration. The heat shield that protects the spacecraft has to handle temperature variations that would destroy most materials, going from the coldest conditions of space to temperatures exceeding 1,000 degrees within hours as the spacecraft swings around the Sun. What the probe has been finding is that the solar wind is more complex and more structured than the relatively smooth stream the models assumed. There are discrete, intense bursts of magnetic activity called switchbacks, reversals of the magnetic field direction that occur on small scales throughout the inner solar wind, and which were completely unexpected before the probe started measuring them. These switchbacks may be important for understanding how the solar wind gets accelerated, and they are one example of how direct measurements in previously unexplored regions are consistently surprising researchers who thought they understood the broad outlines of the system. This pattern of finding more complexity and more structure than expected when you actually go look at something directly runs through virtually every area of solar and space physics. It is a recurring theme in the scientific process, and it should inform how we hold the current understanding of the coronal hole situation. We know a lot. What we have learned in the past decade is extraordinary compared to what we knew 20 years ago, and there is almost certainly significantly more complexity in the current picture than even the most sophisticated current models capture. One of the places that complexity shows up most starkly is in the relationship between the Sun and the broader heliosphere, the vast bubble of solar influence that extends far beyond Earth and the inner planets, encompassing the entire solar system and gradually fading into the interstellar medium at distances that are genuinely hard to conceptualize. The Voyager spacecraft, both of them, have now crossed the heliopause, the boundary where the solar wind finally becomes too weak to push back against the interstellar wind. Voyager 1 crossed it in 2012. Voyager 2, on a different trajectory, crossed it in 2018. They are the only human-made objects that have ever left the heliosphere and entered interstellar space, and the measurements they made at the boundary revise some of the assumptions about what that transition region looks like. The heliopause is not a clean, sharp boundary. It is a turbulent, structured transition zone where solar wind and interstellar medium are in a complex interaction, and the nature of that interaction affects how interstellar particles penetrate into the solar system, which in turn affects the background radiation environment throughout the heliosphere. All of this is connected. The same physics that governs the coronal holes pointing at Earth right now also governs the structure of the heliosphere at its outer edge, billions of kilometers away. Solar activity levels affect how strongly the Sun pushes against the interstellar medium, how much of the heliosphere fluctuates in size and shape across the solar cycle. The entire system breathes with the Sun's 11-year rhythm. Understanding this breathing matters for understanding the radiation environment that any interstellar mission would encounter, for modelling the cosmic ray flux that reaches Earth, and for putting our solar system's environment in context relative to other stellar systems that might host habitable planets. The same processes we see operating around our Sun are presumably operating around most stars, and understanding the detailed physics of our own star's heliosphere gives us the tools to think about what stellar environments might be like around other stars with different activity levels and different magnetic cycles. The question of whether a star's activity level and cycle intensity matters for the habitability of its planets is one that has moved from speculation to active observational science in the past decade, and it connects the immediate story of coronal holes over Earth to one of the most profound questions in modern astronomy. When astronomers talk about habitable zones, the range of orbital distances from a star where liquid water could exist on a planet's surface, the calculation is primarily based on temperature, on the amount of stellar energy received at that distance. But the story we have been telling about Earth's relationship with the Sun shows that temperature is far from the only relevant factor. A planet could be in the right temperature range to have liquid water and still be stripped of its atmosphere by stellar wind, or baked by intense ultraviolet radiation, or bombarded by particle radiation at levels that prevent the development of complex surface life. The question of how active a star is, how intense its stellar wind, how frequently it produces major eruptions, matters enormously for habitability in ways that go beyond simple temperature calculations, and the answer turns out to be highly dependent on the type of star. Our Sun is a relatively calm middle-aged star by stellar standards. It has been in a stable phase of hydrogen fusion for about 4.5 billion years and has roughly 5 billion years left. In the context of stellar activity, it is a fairly well-behaved star. It produces coronal holes and solar flares, and the occasional significant coronal mass ejection. But it is not producing the kind of extreme activity that some other types of stars exhibit routinely. The most common type of star in the galaxy, by a significant margin, is the type called red dwarfs, stars that are smaller, cooler, and less luminous than the Sun. Because they are less luminous, any planet in their habitable zone has to orbit very close to the star to receive enough warmth to maintain liquid water. And this close orbital distance creates a problem that has become more apparent as the study of stellar activity and planetary habitability has advanced. Red dwarf stars are, in general, significantly more active than Sun-like stars in ways that matter for planetary habitability. They produce intense flares much more frequently. They generate powerful stellar wind that flows close to their orbiting planets, because those planets are so near the star. The ultraviolet and X-ray output of red dwarf flares can be orders of magnitude more intense than typical solar flares, hitting their close-in planets with doses of radiation that would be lethal to surface life on Earth within hours. Some of the red dwarf systems that have attracted the most attention as potentially habitable are now understood to be located around extremely active stars that are producing flares multiple times per day. The atmospheres of planets around these stars, if those planets even have atmospheres, are being subjected to a constant, intense barrage. Whether life could evolve and persist under those conditions is genuinely unknown. It might be possible in subsurface environments, protected from the radiation. It might be possible if the planet has a strong magnetic field similar to Earth's. It might not be possible at all if the stellar activity is severe enough to strip atmospheres on timescales shorter than the time needed for life to get established. This is why the current understanding of coronal holes and solar wind and geomagnetic interactions is not just practically important for protecting our own infrastructure. It is also scientifically important for understanding whether life is likely to be common or rare in the universe. The detailed physics we are learning from studying our own star's activity becomes the foundational knowledge for assessing the habitability of other stellar systems. There is a specific research program that connects these two stories in an interesting way. Scientists studying stellar activity across many different types of stars have been using some of the same conceptual frameworks developed for understanding space weather at Earth to assess the space weather environments around other stellar systems. Just as we model the zone of Earth's orbit where solar wind conditions are particularly intense versus relatively calm, researchers are now beginning to model the stellar wind environments around nearby star systems to assess which orbital zones might be more or less protected from stellar activity. What they are finding is that Earth's situation, with a calm star and a substantial planetary magnetic field that has been maintained through most of the planet's history, looks increasingly like it may be somewhat special, not necessarily unique in the entire galaxy, but perhaps unusual in ways that matter for the development and persistence of complex life. our magnetic field is powered by the churning of liquid iron in our outer core, and that churning is driven by heat flowing out from the inner core, which is itself cooling over geological time. The processes that maintain a planetary dynamo and hence a magnetosphere depend on the internal structure and thermal evolution of the planet. Not every rocky planet in a habitable zone will have and maintain a strong dynamo throughout its history. Mars is the obvious cautionary example. Venus, our other inner solar system neighbour, also appears to lack a global magnetic field, though for different reasons than Mars. The conditions that allowed Earth to maintain an active dynamo for billions of years, through the period when life was evolving, may reflect a somewhat particular combination of planetary size, composition, and the presence of the Moon, whose tidal interaction with Earth affects the dynamics of its interior. This is an area of ongoing research and significant uncertainty, but the broad picture is that the combination of circumstances that makes Earth habitable is more specific than simple distance from the star. None of this changes what is happening over the next several days with the coronal holes. But it provides a context for why watching this event carefully is not just about protecting power grids and satellites in the immediate term. Every geomagnetic storm provides data. Every measurement of how Earth's magnetosphere responds to different solar wind conditions refines the physical models. Those refined models feed into our understanding of planetary habitability more broadly, and that understanding informs one of the most fundamental questions humans have ever asked. Are we alone? The answer to that question, if it ever comes, will in part depend on the work being done right now by the people running the space weather monitoring networks, comparing their instrument readings to their models, figuring out where the predictions were right and where they were wrong, and refining their understanding of the dynamic electromagnetic relationship between a star and its planets. Let us come back to Earth, literally, and look at some of the specific things happening right now that are not making mainstream news, but that are directly relevant to the current solar activity. There is an ongoing and fascinating experiment involving the natural world's response to geomagnetic activity that has been producing surprising results. For decades, researchers studying animal navigation have known that many species use Earth's magnetic field as a compass. Homing pigeons, migratory birds, sea turtles, salmon, certain bacteria, and several other organisms all have varying degrees of magnetoreception, the ability to sense the direction and intensity of the magnetic field and use it for navigation. The mechanisms vary. Some organisms appear to use tiny crystals of magnetite in their bodies as biological compass needles. Others may be using a quantum mechanical effect in certain light-sensitive proteins in their eyes, detecting the magnetic field through subtle changes in how chemical reactions proceed depending on field direction. What has been emerging from the research over the past decade is that geomagnetic disturbances, including the kind caused by solar activity, genuinely disrupt animal navigation in measurable ways. During periods of elevated geomagnetic activity, homing pigeon races show dramatically increased rates of birds failing to return home. Migratory birds have been documented making navigation errors during geomagnetic storms. Even whale strandings show a statistical correlation with elevated geomagnetic activity in some datasets, suggesting that the navigational systems these large marine animals use to orient themselves in the ocean may be affected during storms. This is not a dramatic effect that kills animals or causes mass navigation failures. It is a subtle degradation in navigational accuracy that is measurable only at the population level. But it is a reminder that the electromagnetic environment affects biological systems, not just electronic ones. Life on Earth evolved in the context of Earth's magnetic field, and the field's variability is part of the natural environment that organisms experience. The implications extend into questions about geological deep time that are genuinely interesting to think about. Earth's magnetic field has reversed direction multiple times over geological history, with north and south magnetic poles exchanging positions on timescales of hundreds of thousands of years. During these reversals, which take anywhere from a few thousand to tens of thousands of years to complete, the field passes through a period of dramatically reduced intensity and complex multipolar structure. The magnetospheric protection that Earth currently enjoys during normal conditions is significantly reduced during a reversal. A reversal in progress would mean a much more intense space weather environment at Earth's surface, with increased cosmic ray penetration, potentially more intense effects from solar storms on the upper atmosphere, and the kind of navigational disruption for organisms that we see in mild form during modern geomagnetic storms, but persisting for thousands of years rather than days. The geological record preserves evidence of these reversals in magnetically sensitive materials, and the record appears to show that reversals do not cause mass extinctions. Life has survived dozens of them over the past few billion years, but the details of how the biosphere responds to extended periods of reduced geomagnetic protection are still being worked out. And there are some statistical hints in the fossil record of elevated extinction rates or evolutionary turnover around some reversal events, though whether that is causal or coincidental remains debated. We mention this not because a geomagnetic reversal is imminent, though the field has been weakening and showing some signs of instability over the past few centuries that have some researchers paying attention, but because it illustrates the deep time context within which the current solar activity story is embedded. The relationship between the Sun and Earth's magnetic environment has been shaping life on this planet for its entire history, in ways we're only beginning to understand in any detail. The more immediate deep time context is the one we can actually document from historical records, and the historical record of extreme solar events is both more complete and more sobering than many people realize. The 1859 event, the one known as the Carrington event after the British astronomer Richard Carrington, who observed the solar flare that produced it, is often cited as the benchmark for extreme space weather. It produced telegraph system failures, visible auroras at tropical latitudes, and geomagnetically induced currents so strong that some telegraph operators could send messages using only the induced current with their batteries disconnected. By the best estimates from the historical record of magnetic observatory data, it was an event that significantly exceeded anything recorded since. But Carrington 1859 is not the largest event in the long-term record. When researchers analyze tree ring data and ice cores for the chemical signatures of extreme solar particle events, they find evidence of events substantially larger than 1859 in the more distant past. There is a particular signature in tree rings and ice cores from around the year 775 CE that corresponds to a solar particle event that was, by some estimates, many times larger than the Carrington event in terms of the total energy delivered to Earth's upper atmosphere. There are other large signatures in the record, from around the year 994 CE and from around 660 BCE. These were not events that civilizations wrote about in any way that preserved detailed accounts, partly because there was no electrical infrastructure to be dramatically affected, and partly because even the aurora associated with such an event might have been interpreted as a sign or omen rather than a physical phenomenon. But the physical record is there in the chemistry of the atmosphere, preserved in ice and wood, telling us that the Sun has been capable of producing events significantly more energetic than anything we have experienced in the modern era. The frequency of these extreme events is not well constrained. The best estimates from the long-term record suggest that events comparable to, or larger than Carrington, might occur once per century or so, and events comparable to the 775 CEE event might occur once per 1,000 years or longer. But these are statistical estimates from a record with significant uncertainties, and the unpredictability of the Sun's magnetic dynamics means that even these rough frequency estimates should be treated with humility. What they tell us unambiguously is that the solar system is capable of producing space weather events that would be catastrophic for modern civilization, and that the probability of experiencing such an event over the next century is not negligible. It is not a certainty, and it is not imminent, but it is real, and the gap between what would happen and what we are prepared for is significant enough that it deserves serious attention. The gap between risk and preparation has been closing, though more slowly than the research community would like, and understanding how that gap is being closed requires looking at some of the specific technical and policy work that has been happening quietly over the past decade. On the technical side, the most important recent development is probably the increased focus on geomagnetically induced current modelling at the level of individual power grid elements. For years, the approach to GIC risk was largely top-down, estimating the regional current levels that a storm of given intensity would produce and assessing whether transmission lines would be affected. The more sophisticated current approach attempts to model, at the level of individual transformer stations and transmission lines, what the induced current would be during specific storm scenarios, taking into account the local geology, the specific characteristics of the hardware, and the configuration of the grid. This kind of detailed modelling has revealed that the risk is not evenly distributed. Some transformers in some locations are much more vulnerable than others due to the combination of their physical design, the electrical characteristics of the grid they are connected to, and the geological properties of the bedrock under them. High-resistance bedrock like the ancient crystalline rock of the Canadian Shield or the Scandinavian Shield concentrates geomagnetically induced currents in the conducting infrastructure above it rather than allowing them to dissipate into the ground. A transformer sitting on top of that bedrock during a significant storm receives a much higher induced current than an equivalent transformer sitting on sedimentary rock with higher electrical conductivity. Knowing which specific transformers are most vulnerable allows grid operators to prioritize those assets for protection and monitoring, and to develop specific operating procedures for those grid segments during storm events. This targeted approach is more practical than trying to harden every element of every grid, which would be prohibitively expensive, and it allows the available resources for resilience improvement to be concentrated where they will have the most impact. On the satellite side, the resilience improvement has come partly through better engineering standards for new satellites, with more robust shielding and design approaches that reduce single event upset rates from energetic particle strikes, and partly through improved operational procedures. Satellite operators have developed more sophisticated conjunction analysis processes that account for the increased orbital prediction uncertainty during geomagnetic storms, and they have procedures for entering safe modes or reducing operations during elevated space weather conditions. The positioning of satellites also matters. Operators who choose to place satellites at orbital altitudes that happen to sit within the outer radiation belt are accepting a much higher radiation environment baseline than those who operate in lower orbits below the belt, and this trade-off is increasingly well understood and factored into mission design. There has also been meaningful progress on the policy and coordination side. The development of national space weather action plans in the United States, United Kingdom, and several other countries over the past decade has moved the conversation from scientific warning to operational planning in government circles. These plans identify the critical infrastructure dependencies, establish information-sharing protocols between space weather forecasters and infrastructure operators, and set priorities for resilience investment. The challenge, and it is a real one, is that the political time horizon for infrastructure investment is typically much shorter than the return period for extreme space weather events. Politicians and budget planners think in terms of election cycles and annual budgets. The return period for an event like 1859 is measured in decades to centuries. Spending significant money today to protect against something that might not happen in any given politician's tenure is a hard sell, even when the potential consequences are genuinely catastrophic. This is not unique to space weather. It is a fundamental challenge in any domain where the worst-case scenarios are low-frequency, high-consequence events, pandemic preparedness, volcanic eruption planning, large earthquake resilience, asteroid impact mitigation, all face the same structural challenge of mobilizing resources for risks that feel distant and hypothetical until they suddenly become very immediate and real. The communities working on these problems have learned from each other. The frameworks developed for pandemic preparedness have influenced how space weather risk is communicated and planned for. The experience of large earthquake events in Japan and elsewhere has informed how infrastructure resilience planning is approached for space weather scenarios. The cross-pollination between these different catastrophic risk domains is producing better thinking about how to communicate these risks in ways that motivate action without provoking either panic or dismissal. One of the most useful conceptual tools that has emerged from this work is the scenario-based approach to risk communication, which focuses less on abstract probability estimates and more on concrete descriptions of what specific event levels would mean for specific aspects of daily life. Rather than saying there is a 5% chance of a major geomagnetic storm in the next decade, the more effective communication goes through what a KP7 storm means for GPS accuracy, for HF radio communications, for power grid operations, and for satellite services in enough concrete detail that the people responsible for those systems can make specific decisions about preparation. This approach has been more successful at getting infrastructure operators to actually implement protective measures, because it gives them something specific to prepare for rather than a probability estimate that is too abstract to drive operational planning. And the moderate events, the KP5 and 6 storms that happen several times per solar maximum, serve as real-world rehearsals for the scenarios that have been described, allowing operators to validate that their protective measures are actually working as intended. The current coronal hole event, if it reaches the higher end of the current forecast range, will be one of those rehearsals. The first coronal hole event a month ago was another. Each one provides data, tests procedures, identifies gaps, and incrementally improves the overall resilience of the systems that millions of people depend on without knowing it. Let us talk about one specific area of resilience that rarely gets discussed in the popular coverage of space weather, but that represents one of the more interesting intersections between solar physics and everyday life. It involves the technology that most people interact with constantly, that has become the foundation of modern navigation, logistics, agriculture, and financial systems, and that is specifically vulnerable to the kind of ionospheric disruption that geomagnetic storms produce. The global navigation satellite systems, of which GPS is the American version, and there are equivalent systems operated by Russia, Europe, and China, work by having satellites broadcast precisely timed signals from space. A receiver on the ground or in a device calculates its position by measuring the time it takes signals from multiple satellites to arrive and triangulating the position based on those timing differences. The accuracy of this process depends on knowing precisely how fast the signal travelled through every layer of the atmosphere between the satellite and the receiver. In clear, calm atmospheric conditions, this calculation is straightforward because the ionosphere through which the signal travels has well-characterized refractive properties that can be corrected for. But during geomagnetic storms, the ionosphere becomes turbulent. The density of electrons in the ionosphere changes rapidly and unevenly as the storm deposits energy from the magnetosphere into the upper atmosphere. The signal bending and delay become irregular and difficult to correct for, and the positioning accuracy of any navigation system relying on these signals degrades. The degradation is not uniform across all users. The effects are most severe at high latitudes, close to the polar regions where geomagnetic activity is strongest, and at low latitudes near the equator, where a different type of ionospheric disturbance called equatorial plasma bubbles tends to occur during disturbed conditions. Mid-latitude users experience intermediate effects, but even mid-latitude GPS accuracy can degrade from the typical sub-meter precision to errors of several meters or more during moderate geomagnetic storms, and the degradation can be larger and more erratic during severe events. For most casual navigation uses, a few extra meters of positioning error is annoying but not consequential. Getting to an unfamiliar restaurant in a new city with slightly degraded GPS is a minor inconvenience. But there are domains where meter-level positioning accuracy matters enormously. Modern precision agriculture relies on GPS-guided equipment to plant, fertilize and harvest with centimeter-level accuracy, maximizing yields by planting rows as close together as the machinery can manage without overlap. A geomagnetic storm that degrades positioning accuracy during planting season can have measurable effects on crop yields. Aviation instrument approaches, particularly the systems that allow aircraft to land in low visibility conditions using GPS guidance, have strict accuracy and integrity requirements that can be compromised during disturbed ionospheric conditions. Aviation authorities issue notices to airmen when space weather conditions are expected to degrade navigation system performance, and some approach types may be suspended until conditions improve. Construction and surveying equipment using high-precision GPS can produce errors that compromise the quality of whatever is being built or measured. High-frequency trading systems that rely on GPS timing for synchronizing transactions across distributed financial infrastructure can experience timing anomalies during ionospheric disturbances. The supply chain tracking systems that move goods through ports and warehouses depend on GPS. The dredging and positioning systems that allow large ships to navigate narrow channels use GPS. None of these dependencies are obvious from the outside. The connection between a coronal hole on the Sun and the accuracy of the equipment planting wheat in Kansas is not one that most people would ever think about. But the connection is real, and it runs through the ionosphere in the same way that the northern lights do, just less visibly. The research community studying ionospheric space weather effects has made substantial progress on forecasting these impacts. Dedicated networks of sensors measure ionospheric conditions in near real time, and increasingly sophisticated models can predict how specific storm conditions will affect navigation signal quality at different locations. Some navigation systems, particularly the high-precision versions used in aviation and surveying, incorporate corrections from ground reference networks that can partially compensate for ionospheric disturbances, but the corrections work better for gradual, predictable changes than for the rapid, irregular turbulence of a significant geomagnetic storm. The next generation of navigation satellite systems being developed and deployed by multiple countries incorporates signals at multiple frequencies specifically to allow receivers to better characterize and correct for ionospheric effects, and this will substantially improve positioning accuracy during disturbed conditions compared to current single-frequency systems. But the transition takes time, requiring both new satellites and updated receiver technology, and during the transition period the vulnerabilities of the current infrastructure remain real. There is something almost philosophical about this particular dependency. We have built navigation systems that rely on extremely stable atomic clocks in space, broadcasting precisely timed signals through an atmosphere that is fundamentally affected by the same sun that the system is in some sense trying to work around. The ionosphere is not an obstacle that was stupidly overlooked in the design of GPS. It was known from the beginning and the system was designed with corrections for it. But the corrections work within a range of ionospheric variability, and extreme space weather takes the ionosphere outside that range. This is a pattern that appears throughout the technological resilience story. Systems are designed with known variability in mind, and they work well within that designed range. The failures, when they occur, typically happen at the boundaries of the designed range, in conditions that were understood to be possible, but were treated as acceptable tail risks rather than design requirements. The question of where to set the boundaries, how extreme an event to design for, is always a trade-off between cost and risk, and the right answer is never obvious in advance. The people who spend their careers thinking about exactly this kind of question, the scientists and engineers working on the boundary between solar physics and infrastructure resilience, have developed a perspective on risk that is worth conveying, because it is quite different from the way these risks are typically discussed in popular media. The popular framing tends to oscillate between two modes. Either a solar event is being treated as a normal, manageable occurrence, a nice aurora story, or it is being portrayed as an impending civilization-ending catastrophe. The researchers who understand the system best tend to occupy a more uncomfortable middle position. They're genuinely concerned about specific tail risks in ways that go beyond routine monitoring and careful operations. They know the historical record shows that the sun has produced events dramatically more severe than anything we have experienced with modern infrastructure. They are aware of the specific gaps in current protection measures, and they are also aware that the probability of experiencing the worst-case scenario in any given year is low, that the systems we have built are more resilient than they might appear from a distance, and that the right response is sustained, systematic improvement rather than either complacency or panic. This position is epistemically correct but rhetorically difficult. It requires holding genuine uncertainty and genuine concern at the same time, without collapsing either into false reassurance or false alarm. The researchers who are best at this tend to communicate by focusing on the physical mechanisms, explaining in concrete terms what the system does and how it responds to different inputs, and letting the implications follow naturally from that understanding rather than leading with emotional framing. That is essentially the approach this entire story has been trying to take, starting with the physical reality of what a coronal hole is and following the chain of physical consequences out to where they actually touch everyday life. The goal is not to make you frightened of the sun. The sun is doing what it has always done. The goal is to make the invisible visible, to show you the electromagnetic relationship between our star and our planet that is always in operation, that shapes your daily life in dozens of ways you may never have thought about, and that occasionally produces the kind of events we have been discussing in the past few days. There is a specific aspect of this story we have not yet touched on that I want to spend time with, because it connects the space weather narrative to something that is genuinely new and genuinely interesting in the current moment, something that changes the practical significance of everything we have been discussing in ways that were not true even a decade ago. The number of satellites in orbit around Earth has increased dramatically in recent years, driven primarily by the deployment of large commercial constellations designed to provide global broadband internet service. Where there were roughly a few thousand active satellites in orbit in 2015, there are now something closer to 10,000, with plans filed and partially approved for constellations that would push that number to many tens of thousands over the coming decade. This is the most rapid increase in the population of operational spacecraft in the history of spaceflight, and it is happening in low Earth orbit, the zone most directly affected by geomagnetic storm-driven atmospheric expansion. The practical consequences of this orbital crowding for space weather resilience are both straightforward and complex. The straightforward part is that there are simply far more satellites now that can be affected by atmospheric drag increases during geomagnetic storms, far more conjunction analysis calculations that have to be rerun when the atmospheric model suddenly changes, and far more orbital predictions that become less reliable during disturbed conditions. The operational burden on satellite operators and on the collision avoidance systems that track all of these objects increases substantially during every geomagnetic storm in proportion to the number of objects in orbit. The complex part is that the loss of even a fraction of these satellites during a severe space weather event would have consequences for the global communications infrastructure that are qualitatively different from what a similar event would have meant a decade ago. When there were a few hundred communication satellites in low Earth orbit, the loss of dozens of them would have been expensive and disruptive but manageable. If there are eventually tens of thousands, and they become load-bearing infrastructure for internet access, agricultural communications, financial transactions, and emergency services in ways that current infrastructure already is in some regions, the consequences of a severe geomagnetic storm that produces the kind of atmospheric expansion that took down a batch of low-orbit satellites a few years ago could be much more significant. The resilience of this new satellite infrastructure to space weather is being actively worked on by the companies building these constellations, partly because the events of recent years have provided concrete, expensive lessons, and partly because the regulatory environment is beginning to require explicit consideration of space weather risk in constellation, design, and operations. The design of individual satellites has improved. The operational procedures for managing constellations during elevated space weather conditions are being refined. But the overall vulnerability of global communications infrastructure to a severe space weather event has increased substantially over the past few years, simply because of how much more of that infrastructure is now space-based. This is one of the less discussed dimensions of the rapid commercialization of space. The benefits of satellite constellations for global communications, for remote sensing, for scientific research, for the developing world that has never had reliable terrestrial internet infrastructure, are real and substantial. But these systems exist in the space weather environment, and decisions made about how to design, operate and protect them have implications for the resilience of global infrastructure that extend well beyond any individual company's bottom line. The regulatory frameworks that govern satellite operation are only beginning to catch up to the scale and pace of the current deployment. The coordination mechanisms for managing conjunction risk during space weather events, for sharing space weather data between commercial operators and government monitoring systems, for establishing minimum resilience standards for satellites that provide critical infrastructure services, these are works in progress in the regulatory and policy domain, and the current period of active solar weather is creating urgency around completing them. Meanwhile, the monitoring infrastructure that supports all of this continues to improve. The network of ground-based magnetometers that measure geomagnetic activity in real time has expanded substantially, with particular attention paid to filling in gaps at high and low latitudes where the effects are often most intense. The data from these networks feeds into both operational forecasting and scientific research, and the increasing density of sensors is revealing structure in the geomagnetic response to solar wind conditions that was invisible with the sparser networks of earlier decades. New space-based monitoring assets are also coming online or in development. The continued operation of spacecraft like the Solar Dynamics Observatory, which has been imaging the Sun at high resolution across multiple wavelengths since 2010, and has generated a dataset of solar imagery that has transformed our ability to track coronal holes, active regions and eruptions in real time, remains critical. The data from that single spacecraft has contributed to more scientific papers and operational forecast improvements than perhaps any other solar monitoring asset in history. The current situation with the two coronal holes is being tracked in real time by the full complement of these monitoring assets, and the data is flowing to forecasting centres and infrastructure operators. The people in the position to do something with that data are doing their jobs. The protective systems that have been installed are in their normal operational states, ready to respond as conditions warrant. What happens over the next several days will add to the body of observational data that is slowly but continuously improving our understanding of the Sun's behaviour and our planet's response. The specific details of how the storm develops, whether the magnetic orientation of the solar wind when it arrives is favourable or unfavourable, for strong coupling into the magnetosphere, whether any additional solar activity develops in the region around the coronal hole, whether the storm produces dramatic aurora displays visible at mid-latitudes or stays in the minor range, all of these will be recorded, analysed, and incorporated into the next generation of forecasting models. There is something I keep returning to when I think about this story and what it means in the larger context. We have had the capacity to see the Sun in the detail required to track coronal holes and monitor their alignment with Earth for only a few decades. Before the ultraviolet imaging satellites went up, before the coronagraphs and the heliosysmic instruments and the in situ solar wind sensors, the Sun was a bright disk in the sky that we knew was active, that we could observe in white light to count sunspots and occasionally catch a glimpse of a flare, but whose deeper structure and dynamic behaviour were essentially invisible to us. The detailed, real-time understanding of solar activity that supports modern space weather forecasting is younger than most of the people working in the field. This matters because it means we are making consequential decisions about infrastructure design and resilience based on a monitoring record that is short relative to the Sun's variability timescale. We have detailed satellite-era observations covering roughly half a century, which is perhaps 4 or 5 solar cycles. The Sun's behaviour over those cycles may or may not be representative of its behaviour over longer periods. The Maunder minimum, that extended period of low activity in the 17th century, had no equivalent in the satellite era. Neither did the cluster of apparently extreme events visible in the deep historical record. We are making decisions about how resilient our infrastructure needs to be based on a dataset that almost certainly undersamples the full range of solar behaviour. The models we use for risk assessment are calibrated against a period that may have been relatively quiescent by the Sun's long-term standards. The Carrington event sits near the top of our observational record of geomagnetic storm intensity, but the deep historical record suggests it was not the upper bound of what the Sun can do, only the upper bound of what it happened to do during the period when humans had instruments to record it. Acknowledging this uncertainty is not the same as saying we should expect an extreme event imminently, or that the current coronal holes are more dangerous than the monitoring data suggests. It is saying that the appropriate level of humility about our understanding of the tail of the distribution of solar events is higher than the confident extrapolations from a few decades of data might imply. The researchers who study the historical record of solar activity using tree rings, ice cores, and ancient accounts of auroras are doing some of the most important work in solar physics, precisely because they are extending the effective length of our observational record backwards in time, giving us a better sample of the distribution we are actually dealing with. The results from that work have consistently shown that the modern era is not a reliable guide to the full range of solar behaviour, and that planning for resilience based only on the modern record systematically underestimates the tail risk. This is the underpinning reason why events like the current coronal hole episode matter beyond the immediate question of whether we're going to see some nice auroras this week. They are reminders that the Sun is a dynamic, variable star. They are opportunities to test and improve the systems we depend on. They are part of an ongoing conversation between the scientific community, the infrastructure community, and the public about how much risk we are willing to accept from a source of hazard that is both well understood in its mechanisms and poorly constrained in its extremes. That conversation is happening right now in the data flowing from monitoring satellites, in the forecasting centres running their models, in the operations centres where infrastructure managers are deciding whether to take precautionary actions based on the current forecasts. It has been happening continuously since the first geomagnetic storm was recorded, and it will continue happening for as long as we have a civilization sophisticated enough to conduct it. The aurora, if it appears this week, is the visible tip of all of this. It is the photon signature of magnetic reconnection happening tens of thousands of kilometers above your head, of electrons spiraling down field lines into the upper atmosphere and exciting nitrogen and oxygen molecules to luminescence, of the magnetosphere doing its fundamental job of absorbing the energy from the solar wind, and finding a place to put it that is not your power grid or your satellite. It is beautiful in the way that a working system is beautiful when you understand what it is doing, and the coronal hole that generated the solar wind driving that display is doing what coronal holes have done for as long as the Sun has had the structure to produce them, which is at least as long as complex life has existed on Earth. Long before there was anything on this planet capable of being disturbed by it, the Sun was opening these quiet, dark regions in its magnetic field and pouring fast solar wind through them toward whatever happened to be downstream. Earth happened to be downstream then, and it happens to be downstream now. The difference between then and now is not the Sun. The Sun has not changed. The difference is us. We built cities and grids and satellites and networks and all of the intricate, interconnected infrastructure of a technological civilization, and we built it in the electromagnetic environment of a solar system that operates on the Sun's schedule, not ours. The Sun does not negotiate, and it does not know we are here. What we have that nothing else in the history of this solar system has ever had is the ability to watch, to measure, to understand, and to adapt. Not perfectly, not with certainty, but with increasing sophistication and with the accumulated knowledge of generations of researchers who stared at the same star through better and better instruments and slowly, carefully, figured out what it was doing and why. The 2 coronal holes open on the Sun right now are part of that continuing education. The measurements being made, the forecasts being issued, the decisions being made by infrastructure operators who are acting on the best available information, all of it represents the current state of a practice that is still relatively young and still improving, but that has already accomplished something remarkable. It has made the invisible visible, it has given warning where there was none before, and it has begun to build real resilience into systems that once were simply at the mercy of what the Sun decided to do on any given day. Watch the northern horizon this week if the skies are clear where you are. The light you might see, if the storm develops as the models currently suggest it might, travelled 93 million miles and passed through a planet-sized electromagnetic shield to reach you. It is photons generated by the oldest physics in the universe, in the place where the Sun's reach ends and Earth's protection begins. That boundary is not a fixed wall. It moves, it breathes, it responds to what the Sun sends at it. And right now, it is working a little harder than usual, because something opened up on the surface of a star 8 light minutes away, and the physics of the universe conspired to aim it roughly in our direction. That is the situation, and now you know what it actually means.